Thank you. So this is very much work in progress with Will Bird. And it started in this beautiful setting in Cambridge, England, where I'm now based, and Will was visiting. And we were just brainstorming ideas of course, using relational programming, which is what he does. And some of you might know him in the Clojure community because of that. And even though core logic is not that hype anymore, I will still do some core logic in this talk, and I will also mix it up with some SMT. So let's first decrypt this acronym. So what is SMT? It stands for Satisfiability Modulo Theories. And this is what I want you to take away from this talk, is that there are some off-the-shelf solvers that exist now that you can use to do quite a lot of low-level work that you need if you have some constraints to solve. And it starts all with satisfiability, so just Boolean constraints, and then modulo theories, because you can add arithmetic constraints, uninterpreted function constraints, and even more things. And I'll show some examples of that. And then the CLP, which you might know from core logic, is constraint logic programming. And here in particular, we will stick to the relational subset where we want everything to be pure and just programming by specifying relations instead of functions. And we will do a lot of coding. But just to motivate why would you want to combine these two things first, when you have a search strategy like this, often when you're solving constraints, you're searching. And often it's good to have a sort of high-level strategy that then guide low-level solving. So here, for example, what this depicts is that you have a point where you have a choice between V1, V2, and V3, and then you have a search tree for the rest, and you might explore it in different ways. So one way, which would be what Prolog does, is to go depth first and explore this branch exhaustively and then come back up. And this is very nice for memory consumption because you can just push and pop things in a stack sort of fashion. Or you could go breadth first, or you could do what Mini-Cameron and Core Logic do, which is do a sort of, not a fair, but a complete search, where you always do a little bit of everything. OK, so we'll do a lot. I'll show you a lot of code and show you how things run. And all the code I will show will have this form. So it will always be S expression, but it will not always be Clojure. So first, at the low level, I will use SMT-lib, which is a standard to specify your programs to be solved by SAT solvers, or SMT solvers, rather, more broadly. And then, of course, we'll do some core logic. And here, what I'll do is that I'll hook up the low-level SMT solving with the high-level core logic and see what we can get there. And then all our work was actually done in Mini-Cameron, which recently has been sort of at the forefront of relational programming, more so than Clojure. And there's even the second edition of the reason schemer that came out this year. OK, and I'll come back to these references at the end. Let us jump to code now. OK, so for SMT, this is what an SMT program looks like. I'm just going to make this full screen. A very simple one where we're just saying we have some constant Boolean, and then we assert this proposition to be true, or this Boolean to be true, and then we can check whether it can satisfy this. So if I run this, just calling Z3, it says, yes, I can satisfy this. And I can even ask it, well, how would you satisfy this? So I say, get the model, and then it tells me, well, the model is that P is true. And notice that here it sort of defined it as a function, because this declare const is just syntactic sugar for this. So it gives you an answer. What about if I now assert not P at the same time? Let me remove that part. Then here it says, well, I can satisfy this. So this is like the basic sort of Boolean that you can have. And you can already, just with this part, with the satisfiability part, go quite far. So another example is to say, is this conjecture true? And what is this conjecture defining? Any guesses in the audience? Like, what is the sort of the name from the Greeks for this proposition? Yeah, it sort of looks like transitivity. It also looks like function application if you squint, or modus ponens. That's what I was looking for. Yeah. So it's a very old. Yeah, it's true. That's the Latin name. I don't know what the Greek name is. Okay, fair enough. All right. So if I run this proposition, I get unsat because here I've been checking that it's not true. So this is the way you know that something is always true, is you negate it, and then if the negation, you have no way to prove it false, then it's true, right? And if here I just try to do it this way, it's not so insightful. It will just give me, well, if I ask for a model, it will not be so interesting because I'll just get some random model where it says, well, just put P to be true, and actually the rest doesn't matter anyways. If you just, so it's not, so there's ways to use set solvers for satisfiability and unsatisfiability, and that's related to whether you want to prove something, like if you want to prove a tautology versus find a counterexample. Okay, so let me just stash this, but it doesn't really matter. Okay. So let's see what else we can do. So now we get to the part which is beyond set solvers to SMC solvers. We can also work with numbers quite nicely. So this is an example program which I won't even try to find in my head what a correct answer is to that. But I can just ask Z3 for this. And it will give me an example here where I try to set everything to 0 and 8 to 10, and that sort of satisfies all these constraints. And you can see that you have integer constraints and real constraints, and this maybe might look like magic. Can you really satisfy any constraints on number? Well, there are some limitations. So here is like an example. There are some decidable fragments and some things that you might get unknown answers. So if we look at this program now, and run it, it responds quite fast, but it says, for this part, like A times A has to be 3, has to be greater than 3, then I find -8. And for the second part, it sort of found a resolution, but it doesn't always find solutions. So for this program here, you can see that the result was unknown. And that's because it's using multiplication in ways that is very difficult for the solver to handle. So it's good with, when you multiply by a constant, it can usually handle this well. But when you multiply by an unknown, it's quite tricky. So the trick is to try to stay as much as possible in the decidable fragment. But the realization is that even if it's not strictly in that fragment, it usually works quite nicely. So it works much better in practice than in theory, which is rarely the case, but it is the case here. Okay, let's see what else can we do. So there's quite a lot we can do with functions. So one example is abstraction. We can say we have a function that takes an int and return an int, and then we sort of just defined it on this example, and then I can ask for a model of this, and I get, this is the output. So I get, for f, I get a function which has this if statement. This is an if statement, and it's not even doing something useful. It could have just said 1. That would be the same function. So it's not really simplifying things, but at least it can reason with these functions. Another example that is more complicated is with abstraction, where you can sort of even declare abstractly that you have a sort, and you're defining that you have an involution. So f of x is equal to x. And if you look at the output of this, you get something that sort of is trying to do the right thing, where it's saying, okay, I have two sorts of things that are A's, 0, like here it tagged them, and then if I have 0, then I return the 1 part. If I have the one identified one, I return the 0. So you can see that it can reason about these things. Okay, so I showed you a lot of, well, a few things that it can do, and there is more, but I probably won't go into too much detail. There's quantifiers, there's arrays, there's bit vectors, and there's even data types. So what is something that it cannot do? Well, it's not very good at recursion. So this program is written perhaps naively, like if you were trying to encode recursive functions in an SMT, you probably wouldn't use that, I mean, because that clearly doesn't work. But if you try to run this program, it takes quite a while. I guess it times out, and then it returns unknown after a long time. Let's see what happens here. But we can try to read it in the meantime while it's running. So it's just saying I have a factorial. Yeah, so it just returns unknown. So I have some function called fact, and fact of 0 is 1. And then for all n, if n is greater than 0, fact of n is the same as n times fact of n minus 1. And I tried various ways to get this to work with this naive encoding, and for all the cases, I would always get unknown. And this is where the CLP part comes in, because CLP is really good at recursive unfolding and dealing with recursive relations. So let's turn to this now in our outline. So I suppose given the state of the Clojure community nowadays, I was advised to give a refresher on core logic, and I will do that. So, oops. Okay. So as a refresher, in core logic, you always have a run at the top level. And then you can do a run star, or you can run for a few cases. And then you can just have unification variables. So here I say q is equal to 1. Well, I get 1 back. I can also say 1 is equal to 1. And then I get this logic variable back, which says q is not bound to anything, but your problem is satisfied. On the other hand, if I do 1 equal to 2, then I get back the empty list. So the other thing you need to know is this candi, which allows you to branch. So I can say q is equal to 1, or q is equal to 2, and then I get 1, 2. These are the possible answers. And I can also ask for all possible answers, and it's still 1, 2. OK, and the other rite of passage for CoLogic is to define append relationally. So then it will be a function appendo, and it takes 3 arguments. And you have a candi that says if x is the empty list, then ys is yes. Otherwise, you have conso, so this is sort of the relation that allows you to create cons list in the old way. And then so this is saying if xs has x as a first element and xr as the rest, then the resulting output zs has x as a first element and zr and the rest, and we recursively figure out what the rest is. I think that makes sense. Now, if I try to run this, oops, I get an error. And the error is that appendo is such a classic that it's already defined. So I'll rename it my appendo. And then this works. And now the way to use it is to just say, so run star, for example, let's be brave. I can have multiple arguments here, so I'm just going to do this. And if I do this, I get all possible ways of creating a list A, B, C, D, E. OK, so this is for the basics. And then what new features have we added here? So notice that this is only a library that I'm using. So I haven't changed core logic. I just extended it from the inside, and I'll show you how. And so here is an example of a problem that's unsatisfiable. I'm saying, ask the SMT, where I'm saying we have q is equal to 1, or and q equal to 2, and q equal to 3. And this returns the empty list, because it can't satisfy all these constraints at the same time. And then I have other very simple constraints here. But before we go there, let me just show you the code, so then I can explain this a bit better. So the code is in the source. OK, so the code is not very long. It's like the functionality is very condensed. But here, this is just stuff to call out to the SMT solver. So I decided to try it out with CVC4 and Z3, but basically it's just generating a call to the SMT solver. And the SMT solver is already in this S expression list, so it's actually quite easy to read the thing out. We can read out this, whether we have a SAT or not. And we can even read the model. This is a bit crude. It works very well for numbers, and it's sort of work in progress for the rest, but it's just for to show things. We can just read the string back as a model. And one thing we want to do, which we can do now at the high level, is be able to ask not just for one answer. In the SMT solver, you could only say get model. But once we get a model, we can negate it and ask for further possible answers. And we can do this hooking in again onto the laziness of the core logic. So by just saying, OK, get me the first answer, and sorry, here is the loop. So get me the first answer, add this model, and then otherwise try to find another model by negating this one. And then this is sort of the low-level thing where we call the constraint. So it's hooking into core logic parts and all that. So this is how it works. And in my implementation here, I use an atom to keep track of how many output files I'm generating. And this is just useful to explain what's going on. So if we go back to this example, we can try to explain why this fails at the SMT level, because it's sort of like a clean interaction between the SMT level and the core logic level for this to happen. So we see that this fails, and if we look at the output files generated, if we look at, there are so many of them because this is from before. Let me remove them and start over. OK, so if I look for these out file, I get 1 and 2. And you can see that this fails because the one file, sorry, it's here. The one file just asserts whether our unknown is equal to 1, so that's good. And then the second one actually now additionally checks whether it's equal to 2, so this doesn't satisfy. And so this query fails right here at that point. And so the interplay between the SMT and the CLP is sort of works very nicely. And to show a few different examples, we can actually do this query where we have only one result, or we can do a query where we have multiple results. And here I'm only doing around 2 because if I try to do more than that, I mean, there are infinitely many answers. So this is sort of the interface. If I did around 5, that would also work. Oops. And so on. OK, so this is for the core logic part, how we integrated it. And the key idea then is just to have to define a custom SMT-C constraint that is hooking into core logic constraints mechanism. And so here what we see is that when it's invoked, it checks that whether the current stash of things we have is satisfiable. And if not, if it's unsatisfiable, we can fail right there. OK, so what else can we do with this? So we're still sort of experimenting and trying to find a really killer application. We suspect that it will be in symbolic execution and relational abstract interpretation, because that sort of would work with the best of both worlds. But first, let me update you on what has been going on in the mini-Canron world. So a lot has been going on since in the last 5 years in terms of making mini-Canron a really good tool. And what I want, so here these are the basics as before appendo. But what's interesting is the work has been moving on in terms of writing a functional interpreter inside the relational interpreter. So here's an example where Evalo is this interpreter for a scheme-like language inside of mini-Canron. So it's inside the run. And here we're just defining a normal append function as a function, not as a relation, but we can use it back in relational style this way. And we can also, well, this you've probably seen before, that you can have quines where you sort of use the interpreter to say, give me a function that evaluates to itself. So first it gives the Booleans, and then it actually generates a quine properly. So this is all work that Wilbert and others have done. And now in this system that I'm showing, we have additional number constraints and symbol constraints. And what I want to show then is actually the factorial example from earlier. Maybe let me show it in core logic first. So if I look at the factorial example, I can now write it as a recursive relation, and I get the behavior that you would expect. So if you run it sort of with two unknowns, you get, and say you ask for the 7 first results, you get what you would expect. But what's interesting is that you can run it backwards, and you can run it exhaustively backwards. So you do a run star, and this sort of guarantees, it tells you, I know that 2 is the only answer here for what is the factorial of 2. And similarly, you can ask for what is the factorial such that I get 720 and I get 6 is the only answer. So that's pretty nice, and we can even do some like nifty example of like doing RSA cryptography in that system. Okay, so now just to show off a few last examples in the MK land. What's interesting is that we've pushed this idea of working with the functional interpreter defined as a relation. And one thing you can do is sort of say, well, how can I get bar out of here? And then it will sort of give you answers that satisfy this. So I think we've come a long way with playing with the sort of number part of SMTs. And what we want to do next is also play with the other parts that you can do with SMTs. Well, in the spirit of finishing on time, I can maybe just do one more example where we did a bit of abstract interpretation. So we start now not defining a functional language here, but more of a low-level imperative language, and this is sort of what the syntax would look like in scheme expression. And then we can solve this as a symbolic execution problem, so actually find solutions to these. Like here, we're exhaustively saying that there's no solution to satisfy this set of equations, and so on. Okay, so to conclude with some references, so my takeaway is often if you're dealing with constraints in code, it might be a good idea to check SMT solvers, especially if you can stay within the decidable fragment. There's a lot of things you can do, and a good starting point is this tutorial from Z3, and some of the earlier examples that I showed come from there. Another thing, though, is that this article by the author of Z3 also suggests that SMT solvers by themselves are not enough. You want to have a way to guide the search at a high level, and maybe knowing more about your domain, you can do that. And I think this is where the combination with CLP can be interesting. Another solver to look at is CVC4. And that has a very good. It has a good support for set theory. It comes from academia in a way that it's pushing in a different direction as Z3, so it's worth looking at both. The example enclosures are part of this repo that I have called Logically, where I do all sorts of explorations of core logic, including core logic nominal. And for mini-Canron, I would say that a good starting point nowadays is this ICFP 2017 paper that shows all this work on having functional interpreters inside this relational programming model. And for the code on this, using mini-Canron for the CLP SMT, this is the repo. Thank you.